The Atlantic Wall presented a continuous, reinforced concrete barrier. Conventional demolition teams expected heavy losses approaching defended beaches. British planners requested standoff breaching devices using unconventional propulsion. The Admiralty formed the Directorate of Miscellaneous Weapons Development. This small group assessed speculative concepts for rapid obstacle clearance. One proposal involved a large rolling frame carrying bulk explosives. The device would traverse surf, shingle, and anti-tank obstacles. Upon impact, the explosive charge would fracture concrete fortifications. Engineers defined a dual-wheel structure supporting a central drum. Each wheel would have a diameter near 10 feet. The wheels were constructed from layered wooden segments with steel bands. The central drum held the explosive filling and structural axle. Total explosive mass targeted approximately 1 long ton of high explosive. The assembly resembled 2 oversized cartwheels joined by a cylinder. No crew rode within or controlled the device in motion. Propulsion and guidance relied entirely on rocket thrust and balancing. For propulsion, engineers rejected internal engines and mechanical transmissions. They selected disposable cordite rockets bolted around each wheel rim. Each rocket behaved like a standard solid-fuel artillery rocket motor. Combustion of cordite produced high-temperature gases and steady directed thrust. Rockets were mounted tangentially, nozzles pointing rearward relative rotation. When ignited, the combined impulse would spin both wheels forward. The system converted rocket thrust into rotational kinetic energy directly. Linear advance resulted from the rolling contact with the ground. Each wheel carried multiple rings of paired rockets around circumference. The exact number varied between trial configurations and test series. Some prototypes carried over 70 rockets distributed around both wheels. Mounting brackets were steel plates bolted through the wooden felloes. Rockets were secured with clamps and simple steel retaining bands. Ignition used electrical firing circuits linked to a remote panel. Operators could trigger groups of rockets simultaneously via battery power. No in-flight reignition or throttling capability existed for these rockets. Steering requirements produced the most unconventional part of the design. Initial calculations assumed symmetric thrust would produce straight-line motion. However, path correction was required for crosswind and terrain variations. Mechanical steering, such as differential braking, was considered impractical. The wheels were too large for enclosed steering linkages or brakes. Engineers proposed a differential thrust steering solution using auxiliary rockets. Additional rockets could be fired on one wheel, creating yaw. By selectively igniting these, operators hoped to adjust trajectory mid-run. A test plan specified full-scale trials on a Devon beach. The chosen range offered long stretches of flat, hard sand. Access roads allowed heavy transport vehicles to deliver the prototype. Observation stands were set back along the dunes for safety. Military officers, civilian scientists, and local staff attended early trials. Camera crews recorded motion characteristics for subsequent engineering analysis. Medical personnel waited behind protective dunes with stretchers and supplies. Range control established firing procedures and clearance signals using flags. Prototype construction used existing naval workshops and local contractors. Wooden wheel segments came from firms experienced in large cable drums. The central drum shell used mild steel plate, welded circumferentially. Internal bulkheads reinforced the drum and distributed explosive loading evenly. The axle comprised a thick steel tube running wheel to wheel. End hubs interfaced with wooden wheels through bolted steel flanges. Balance weights could be added to counter local density variations. Each component received stencil markings for tracking and configuration control. Engineers specified tolerances for roundness, wheel eccentricity, and axle alignment. Excess eccentricity would amplify vibration and reduce controllability under thrust. Workshop crews checked dimensions using large calipers and improvised gauges. Recorded measurements entered logbooks for later correlation with test footage. Protective coatings included primer paint and bituminous sealants on wood. These coatings reduced water uptake, swelling, and rot during storage. Metal components received simple navy gray paint for corrosion resistance. No ballistic armor was installed on the prototype operational versions. Explosive filling plans assumed cast high explosive poured into the drum. Trials, however, used inert sand or concrete ballast for safety. During early tests, explosive surrogates matched mass but not fragmentation behavior. This allowed full kinetic evaluation without catastrophic detonations on failure. A removable hatch on the drum allowed loading and inspection. Internal braces prevented ballast shifting, which could destabilize rolling motion. Weight distribution achieved approximate symmetry around the rotational axis. Engineers considered off-axis loading a major potential cause of deviation. First full-size trials began with reduced rocket counts for caution. The machine was placed on timber ramps pointing down beach. Electrical leads ran back to a sheltered firing position. On command, operators activated a subset of rim rockets. The wheels accelerated slowly, then gripped the sand surface. Under low power, the device rolled several yards before stopping. This initial run, validated basic ignition and rolling behavior. Observers recorded wobbling and the slight lateral drift under minimal thrust. Subsequent tests increased the number of active rockets per run. Additional igniters were wired, and more brackets loaded with motors. Engineers monitored for structural flexure at higher rotational speeds. They watched for bolt loosening, rim cracking, and hub distortion. Instrumented stakes along the beach marked expected trajectory and distance. High-speed cameras captured sideways oscillation and wheel deflection at speed. As thrust increased, deviations from predicted linear paths became pronounced. Uneven ignition timing produced surges and yawing moments between wheels. One persistent issue involved inconsistent rocket performance from batch variations. Cordite sticks sometimes burned irregularly, generating fluctuating thrust curves. Some rockets detached early when clamps failed under vibration loads. Detached rockets became uncontrolled projectiles, skimming along the sand. Several embedded themselves near observation areas, causing unplanned evacuations. Range control expanded safety distances after reviewing near-miss locations. Observers were progressively moved further behind dunes and improvised barriers. The range perimeter grew with each additional test series conducted. Steering trials introduced the planned differential thrust solution using auxiliary rockets. Extra rockets were attached asymmetrically on one wheel for control. These used separate firing circuits, triggered after initial acceleration phases. The engineers hoped small corrections would realign the device toward targets. In practice, the added thrust generated abrupt lateral acceleration and yaw. When auxiliary rockets fired, the machine veered unpredictably across the beach. Sometimes it described large arcs, crossing its intended axis entirely. On one occasion, it reversed direction relative to observers' expectations. During a notable trial, the device left its prepared course. It accelerated diagonally toward the dunes and observation parties. Range officers ordered immediate evacuation and took cover themselves. Cordite rockets continued burning while brackets failed sequentially under stress. Live rockets detached, spiraled, and landed among vehicles and equipment. Some rockets embedded in sand, still burning down their remaining charge. Fire crews extinguished small fires in grass near parked trucks. Post-event diagrams showed multiple impact points around designated safe zones. To mitigate instability, engineers modified wheel rims with shallow guide flanges. The intention was to reduce lateral slippage on uneven sand surfaces. These flanges added mass at the periphery, increasing rotational inertia. New balance tests were required after machining and fitting the flanges. Despite modifications, flanges had limited effect on directional control reliability. Soft sand and small stones still deflected paths away from straight lines. Each irregularity interacted with remaining thrust asymmetry and magnified deviation. Steering rockets could not compensate predictably for terrain-induced yaw. Another proposal involved fitting a small trailing stabilizer wheel assembly. Yet this third wheel sat behind the central drum on a frame. The idea assumed a tripod contact pattern would resist rolling oscillations. The trailing wheel incorporated a simple castering pivot for self-alignment. However, the added structure generated new resonance modes at speed. Under rocket thrust, the stabilizer bounced, transmitting shocks into the drum. Bolted joints in the frame exhibited loosening after only short runs. The stabilizer concept was judged ineffective and structurally undesirable. Engineers also evaluated tethered guidance using cables and pulleys ashore. In this scheme, cables attached to the axle on each side. Shore crews would tension cables using winches to correct drift. Practical tests revealed unacceptable lag between deviation and corrective force. Is cable drag reduced achievable range and complicated rocket ignition wiring. Snagging risk on beach obstacles further compromised the tethered concept. The Directorate classified cable steering as operationally unsuitable for invasion. Attention returned to purely rocket-based steering, despite earlier difficulties. Manufacturing documentation recorded recurring issues with wheel joint durability. Repeated high-speed runs loosened bolts and opened gaps between segments. Moisture infiltration then accelerated degradation of the wooden structure. Technicians installed additional through bolts and larger backing washers. Some wheels were partially disassembled, re-glued, and rebanded before reuse. These repairs consumed time and workshop capacity between trial campaigns. Supply officers reported increased demand for hardwood planks and steel bands. Procurement records noted competition with shipyard requirements for similar materials. Rocket Supply introduced its own logistical and bureaucratic challenges. Cordite motors had to meet stringent naval propellant safety regulations. Storage magazines required controlled temperature and humidity to maintain stability. Transport to the beach demanded guarded convoys and secure containers. Every test consumed dozens of motors, often in partial burns. Many rockets ended tests fragmented or buried. Impossible to recover. Accountants recorded high expenditure against experimental weapons budgets. Questions arose regarding cost-effectiveness compared with conventional demolition methods. The test reports were compiled using standard Admiralty technical formats and language. Each run generated a file including diagrams, photographs, and narrative notes. Engineers quantified distance achieved, maximum deviation, and observed structural behavior. They also rated subjective controllability on simple ordinal scales for reference. Cross-referencing between runs attempted to isolate specific configuration effects. However, high variability in rocket performance limited clear statistical conclusions. Weather differences between days further complicated between trial comparisons and extrapolations. The result was a body of data with wide experimental scatter. Safety officers added formal annexes describing hazardous incidents during testing. These annexes listed personnel near misses, flying debris, and errant rockets. One annex described a rocket passing through a redundant safety sign. Another recorded shrapnel damage to an unattended parked vehicle window. Medical entries included minor cuts, bruises, and one sprained ankle. Most injuries occurred during hurried withdrawals rather than direct rocket impact. Nevertheless, the cumulative incident list grew with each successive test day. Safety margins, already stretched, became central in subsequent risk assessments. Risk matrices compared potential operational benefit against testing hazards. Columns listed probability of uncontrolled deviation during an actual assault. Rows enumerated possible outcomes ranging from minor disruption to friendly casualties. The matrices frequently returned ratings in the highest combined risk cells. Planners examined scenarios where the device veered into landing craft zones. They considered burning rockets impacting embarked infantry or stored munitions. Even with increased exclusion distances, these events remained operationally credible. Commanders expressed concern about introducing such uncertainty onto crowded beaches. Parallel work evaluated alternative breaching systems for the same mission requirement. Specialized armored vehicles carried line charges and petard mortars for walls. Scissor bridges and engineer tanks offered more controlled obstacle negotiation. Conventional Bangalore torpedoes, though dangerous to crews, had known behaviors. Comparison memoranda contrasted reliability, cost, and controllability between options. The rolling rocket wheel consistently scored poorly in directional control metrics. Its only advantage was theoretical simplicity of construction and deployment. That advantage eroded as modifications increased complexity and component count. Further attempts to refine rocket mounting arrangements continued across several weeks. Engineers experimented with staggered ignition sequences using timed electrical circuits. The objective was smoother acceleration with reduced instantaneous torque asymmetry. Time relays triggered small groups of rockets in defined succession. However, varying burn durations still produced irregular composite thrust curves. Sometimes late-firing rockets acted when the machine already deviated laterally. These late impulses often amplified, rather than corrected, path divergence. Oscillatory behavior persisted, now in more complex temporal patterns. Data analyses also explored wheel spacing and track width variations. Wider spacing theoretically improved static stability and resistance to tipping. Modified drums used longer axles and reinforced hubs to maintain strength. On test, increased width marginally delayed onset of severe deviation. Once deviation began, however, recovery remained essentially unachievable without steering. Turning radius increased, but uncontrolled arcs still intersected exclusion areas. Broader machines also complicated storage aboard landing craft and transports. Naval staff highlighted stowage limitations and separate logistical correspondence. Environmental conditions at the beach imposed additional uncontrolled variables. Wet sand provided firmer support, but increased rolling resistance initially. Dry sand reduced resistance, but allowed deeper ruts and lateral slip. Small ridges formed by tides deflected wheels without predictable repeatability. Crosswinds acted on the large exposed wheel discs and central drum. Their aerodynamic side forces combined with thrust asymmetry to induce yaw. Engineers documented each day's tide, wind, and surface conditions carefully. Despite detailed logging, they observed no reliably safe operational envelope. Electrical systems supporting ignition also presented vulnerabilities in field conditions. Long cable runs suffered from insulation abrasions and connector corrosion. Salt spray and blowing sand infiltrated junction boxes and control panels. False circuits occasionally produced misfires or unexpected multiple group ignitions. Technicians introduced protective sheathing and additional continuity checks pre-firing. These mitigations added preparation time and personnel around the device. More personnel on the beach increased exposure if the machine deviated. This feedback loop further reduced the system's overall safety rating. The Directorate scheduled demonstrations for senior officers to secure support. Before such inspections, crews performed additional shakedown runs to validate readiness. These internal runs continued to display erratic motion and rocket shedding. Planning staff debated whether limited demonstration success justified operational adoption. Some argued selective footage could frame the concept as controllable. Others pointed to unedited film sequences showing near misses and widespread scattering. Ultimately, decision-makers insisted on witnessing representative unedited behavior personally. This requirement effectively removed any opportunity for curated, positive impressions. When senior observers attended, the machine again behaved unpredictably under thrust. A demonstration run began on a carefully prepared straight launch track. Ignition ignited a majority of rim rockets simultaneously as configured. The device accelerated rapidly, then veered away from marked intended direction. It passed across the tide line, towards areas previously considered safe. Observers retreated behind dunes, while recording continued from partial cover. Several rockets detached, arcing into shallow water and steam clouds. Post-trial summaries adopted restrained language, but highlighted persistent instability. Following these events, the internal memoranda questioned continuation of live trials. Some advocated reverting to scaled models for further theoretical work. Others recommended terminating the project before consuming additional scarce resources. The central question concerned whether remaining time justified further optimization attempts. Invasion planning timelines compressed as Allied preparations intensified for continental operations. Any breaching system still under development faced accelerating decision deadlines. The rocket wheel could not demonstrate reliable performance within available windows. Therefore, its status shifted from promising concept to marginal experimental curiosity. Formal cancellation proceeded through standard administrative channels within the Admiralty. A briefing note summarized objectives, methods, and observed shortcomings succinctly. Attached annexes documented test data, safety incidents, and comparative evaluations. The note concluded that operational deployment risk exceeded anticipated tactical benefit. No further funding would be allocated for full explosive filling trials. Remaining hardware would be retained temporarily for possible limited investigations. Eventually, components were dismantled or scrapped to reclaim workshop capacity. Some footage and documentation were archived within restricted technical collections. The failure, nonetheless, provided information on rocket-propelled rolling structures. Engineers gained empirical understanding of thrust asymmetry effects at large scale. They observed interactions between solid fuel variability and lightly guided platforms. These observations informed more conservative design margins in later projects. Test range procedures were updated to account for unconventional trajectory behaviors. Safety distances for experimental rocket devices increased in official guidance. Documentation emphasized early probabilistic risk assessments for novel propulsion schemes. Subsequent proposals faced higher evidentiary burdens regarding controllability claims. Operational plans for the invasion relied instead on alternative breaching means. Armored engineer vehicles carried shaped charges and petard mortars ashore. Infantry engineers continued to employ conventional explosives under covering fire. Naval gunfire provided additional destructive power against some fortification segments. These methods, while hazardous, offered clearer performance envelopes and control. The commanders accepted known risks rather than introduce experimental rolling explosives. The rocket wheel vanished from active planning documents before final invasion rehearsals. Only scattered references remained in internal research files and anecdotal accounts. No production line was ever established for the device. There were no standardized manufacturing drawings approved for serial fabrication. Workshops produced only a small number of evolving test articles. Tooling remained largely improvised, based on existing naval workshop capabilities. This limited sunk industrial cost compared with other abandoned projects. Inventory write-offs mainly involved rockets already procured for experimentation. These could often be reassigned to other rocket research programs. Thus, its material disposal from cancellation was administratively straightforward overall. In later institutional reviews, the project served as a procedural example. Committees cited it when discussing screening processes for speculative concepts. They emphasized early identification of controllability as a go or no-go criterion. They also highlighted the cumulative nature of small safety deviations over time. The documentation illustrated how minor component failures produced disproportionate consequences. Loose brackets, modest thrust variations, and slight surface irregularities combined. The resulting aggregate unpredictability exceeded acceptable operating tolerances easily. Such lessons entered internal manuals for future weapons development directorates. The machine's physical components disappeared, but records preserved its characteristics. Dimensions, masses, and rocket specifications remained in archived technical papers. Test photographs showed the dual-wheel frame launching from wooden ramps. Still images captured slanted trajectories, broken rockets, and scattered debris. Associated captions use consistent non-emotive terminology and numbered event sequences. In this form, the project persisted only as controlled documentation. Its influence survived as constraints and cautionary notes within bureaucratic systems. The device never advanced beyond experimental status before invasion operations commenced. By the time Allied forces landed, the concept was dormant. No rocket wheels accompanied infantry onto the French beaches that day. Commanders employed breaching techniques with more predictable directional behavior. Yet the dual-wheel rocket apparatus remained an unused solution to obsolescent requirements. It had nearly introduced unacceptable internal hazards to its own forces. Administrative processes ensured its quiet removal before reaching that operational stage. The project concluded as a contained experiment within wartime development structures. Its legacy lay primarily in recorded failures, not battlefield contributions.